Next up in our discussion of coastal siliciclastic environments is the delta environment. Deltas are the interface between the river and coastal settings, and they're characterized typically by a mixture of fluvial, wave, and tidal processes. You've already heard about wave-dominated coastlines and tide-dominated coastlines, so some of those sedimentary structures we'll come back to and I'll mention very briefly towards the end. So deltas are protuberances or bulges in the shoreline where the river enters into a larger water body, like the ocean or lakes. The river will then build outwards, building this subaerial part of the delta, the above water part, but there's also a submarine or below water part of the delta as well. So the subaerial or above water part is called the delta plain. It includes the river channels, which are called distributary channels. It may include shallow bays between those channels called interdistributary bays. It may include beaches or tidal flats or tidal channels, depending on the relative importance of fluvial, wave, and tidal processes on the delta. The shallow marine part of the delta, here shown in the light blue color, which is above wave base, is called the delta front, and the deeper part, at least shown here in blue, down to 50 meters or so, is called the prodelta. It's below wave base, the more distal, deeper subtidal facies here. The delta front and to some extent the prodelta are both characterized by fairly steep gradients. This is especially true in deltas dominated by fluvial processes. So as a result, deltas have this large-scale bed geometry called a clinoform, which is a sigmoidal or kind of S-shaped bed, has flatter topset beds where they bend and become parallel with the overlying flat layers, a steeper foreset, not unlike what you saw in crossbedding, but at a much, much larger scale here, shallowing out toe set beds, and a fairly flat bottom set that again merges parallel with the underlying layers. In the diagram here, the foreset beds the dip is really highly exaggerated. In the real world, the actual dip is just a couple degrees. In the photo here, the yellow lines show the horizontal bedding at the top and the base of the delta front. And between those lines, you can see very gently dipping foreset beds that represent the part of these delta front clinoforms. So we'll talk about the delta environments in order from deepest to shallowest, starting with the prodelta, the deepest part of the delta. It's below wave base, and because it's far away from the sediment source and the energy source, it's characterized by quite fine-grained facies. In fact, the prodelta will often resemble regular offshore facies that you've seen before in terms of regular coastal shelf environments. The main difference is that in a prodelta, you might find slumps. The high sedimentation rates near the river mouth promote slope instability because the sediment accumulates really rapidly. It doesn't have time to compact. It's very water rich. Also, the prodelta is just steeper, and so in a steeper slope, you're potentially able to get slumps that just wouldn't occur in a regular coastal shelf or continental shelf offshore environment. Delta fronts or delta facies always prograde. The shoreline shift in deltas is always regressive. So this is, maybe not always, but it's a very good rule of thumb. Deltas are always progradational. They always occur during system tracks characterized by regression. So this means that the prodelta will be overlain by delta front sediments. And because the delta front is more proximal, it's closer to the source, it's shallower water, it's also coarser grained on average. So as a result, delta successions are pretty much always coarsening upward successions. In the delta front, because it's above wave base, there may be some signals of wave or tide influence. You might see some sedimentary structures like wave ripples or bidirectional crossbeds depending on the type of delta. But sedimentation in the delta front, and also in the prodelta to some extent, is dominantly sourced from plumes of sediment-rich water that comes out of the river mouth. There's two sort of types of plumes characterized by their density. These plumes, called hypopycnal plumes, have a density less than seawater, and then the hyperpycnal plumes have a density greater than seawater. So because seawater is salty and river water is fresh, normal river flow, which contains a little bit of suspended sediment, is typically hypopycnal, and therefore it spreads out in a plume up at the surface of the ocean. As it spreads out, of course, there's friction with the underlying ocean water and the surrounding ocean water, so this plume loses energy and gradually deposits sediment from suspension. This creates a fairly continuous rain of fine-grained hemipelagic sediment, often mud or silt-rich, and you're not going to get sand in suspension out this far. This spreading and loss of energy is not dissimilar from what you saw with turbidity currents as they spread out on the lower fan and lose energy. But when the river floods, so in contrast, when the river's flooding, it's carrying a lot of suspended sediment. There's a lot of sediment, potentially even coarser sediment in suspension, and so this means that sediment water mixture is very dense, often denser than seawater, so it can form these hyperpycnal, or these high-density plumes, and when they flow, because they're denser, they flow as a sediment gravity flow along the seafloor. So it's a turbulent sediment gravity flow. It's basically a turbidite, or a turbidity current, I should say, and it flows down the slope. And so again, these flows will lose energy because of friction with the seafloor and with the water around them, and so they're depositing sediment primarily from suspension, perhaps with some modification by traction flow. So again, these hyperpycnal flows deposit thin, normally graded beds. Because they're turbulent flows depositing suspended sediment by unhindered settling, they are basically turbidity currents, and so they do basically form turbidites, these thin or medium thickness graded beds. These hyperpycnal deposits will be interbedded with the hemipelagic deposits that are formed from the hypopycnal plumes, which are kind of the normal background time. These might be finely laminated or bioturbated, which means mixed up by burrowing, so bioturbated mud. Sometimes the river floods can also get stronger and weaken through time, and so that means that the resulting deposit, the hypopycnal flow, will wax and wane, and that can give you beds that have some inverse grading as the flow strengthens, and then some normal grading or fining as they weaken. So finally, we'll talk a little bit about the subaerial delta plain environment, or the delta plain, not necessarily just the subaerial part of it. This is quite a heterogeneous environment. It can include fairly fine-grained interdistributary bays, coarse-grained distributary channels, terrestrial swampy deposits, tidal channels. A lot of different things can occur in the delta plain environment. Fluvial processes are obviously quite important in deltas, since that's where the river's emptying into the ocean, but the delta plain can actually be heavily reworked by either wave energy or by tidal energy. I'll briefly show a couple examples of wave and tide-dominated deltas later on, but first we should talk about the typical or the characteristic river-dominated delta plains where the fluvial processes dominate. So the main depositional element in the delta plain is something called the distributary mouth bar. As the name suggests, it's a bar that forms at the mouth of the distributary channel. The physics of these mouth bar formations, these distributary mouth bars, depends on the density contrast of the water, frictional interactions, fluvial discharge. There's actually different types of distributary mouth bar. We're not going to deal with that in this class, but just keep in mind that they do exist, different types. But really the key feature of any distributary mouth bar is the rapid deposition of large amounts of sediment. So why does that happen? Well, when the river is flooding, it's carrying a lot of sediment, and it creates one of these plumes of water. And particularly if the sediment concentration is not too high, the density of the river water and the seawater is approximately equivalent. There might be a denser plume that flows along the bottom, but in general it's sort of equal density. So the river water spreads out everywhere as this big, rapidly expanding plume. Because it spreads out really widely and rapidly, it loses energy very quickly due to friction with the bottom, but also with the surrounding seawater. So rapid deceleration of the flow leads to rapid energy loss, which leads to sedimentation. This, as you kind of learn with flow stripping in submarine fans, it's analogous here in that any time the flow loses energy very quickly, it's going to deposit sediment very quickly from suspension. So traction movement of sediment under these rapid depositional conditions, where you're rapidly adding more sediment from suspension, favors the formation of climbing ripples in these mouth bars. Mouth bars may also have erosive bases, and they can often contain erosional reactivation services within the bar because the initial formation occurs with these high-energy flooding events, and the river velocity is going to vary quite a lot. A flood will provide very fast flow, but then normally it's probably fairly weak flow. So here's a picture just of a river-dominated delta with these distributary channels and the interdistributary bays. The lozenge-shaped islands, these sort of pointy islands that are elliptical, they all started as these mouth bars forming at the end of a distributary channel, and then as it accumulated sediment over time, they eventually became exposed subaerially, created more terrestrial or swamp-type deposits. So delta plain sediments are commonly cyclical, as these interdistributary bays fill with sediment and then become abandoned and subside. An interdistributary bay may begin, so the red arrow, for example, this begins with marine mudstones even. Perhaps it might be a lot of organic material because it's very close to the river. And it may even end up with, the yellow arrow is kind of the ending stage of the filling of an interdistributary bay. So the yellow arrow shows one where it's more terrestrial swampy deposits or coastal marshy deposits. In that case, there might be actually coal forming in these environments. The nearby distributary channel may be filled with sandstone, with ripples or even dune cross-stratification, just like you'd see in a river. And there are likely to be crevasse splay deposits within these interdistributary bays from flooding events, again similar to a river. So this is a very sort of mixed marine fluvial system where it can range from marine muds to fluvial sands, crevasse splays, coal deposits from terrestrial swamps even. So I mentioned before that deltas are typically or almost exclusively coarsening upward successions. But that really only applies to the delta front, and so you be cautious because once you get into the delta plain, it actually might be significantly finer grained than the delta front, even though the delta plain is shallower typically and more proximal to the sediment source. The delta plain may have these interdistributary bays with lots of mud or these coal swamps with lots of fine-grained coal. So there can actually be fairly abrupt surfaces. The yellow arrow in the right-hand picture marks one such surface that are denoted by the shift from sand-rich delta front clinoforms below to mud or potentially coal-rich interdistributary bay or swamp sediments in the delta plain. So just finally, although rivers are what is supplying the sediment to deltas, the energy that is moving that sediment around can come from fluvial, wave, or even tidal processes. In a wave-dominated delta, those distributary mouth bars that form at the mouth of the river get heavily reworked into these long, shore-parallel sand ridges. So in this type of delta, the delta plain deposits may look almost exactly like a wave-dominated beach and shore face sediment that you saw before. So you may need to consider the context provided by the overall facies succession, especially the presence of underlying pro-delta and delta front sediments to actually recognize these as delta deposits. Likewise, in tide-dominated deltas, the mouth bars can be reworked into these shore perpendicular elongated sand bodies by the tidal currents in this case. So now here the delta plain may look similar to tidal flat or tidal-dominated estuary facies, maybe bidirectional crossbeds, inclined heterolithic stratification in the channels, and so forth. Again, the context provided by the overall facies succession may be your best clue. So one final note of caution as you consider the sequence stratigraphic context of deltas. Like meandering fluvial systems and submarine fan lobes, deltas, particularly the delta plain, have strong inherent cyclicity. The active lobe in a delta will prograde outwards and accumulate sediment, but eventually the river channel switches locations in a process called avulsion, and the lobe becomes abandoned. The abandoned lobe is no longer receiving sediment, so it subsides because of compaction primarily, and it subsides back into a marine environment. So be cautious about interpreting cycles, especially in the delta plain, as allocyclic base level changes because they could very easily just be normal lobe switching behavior or autocyclic cycles of the delta itself.